All right, my friends, welcome back. As I recall, last time I had given you this product, alpha pinene, that is from pine trees, and I had told you to identify the isoprene units in this structure. And if you want a different view of what this structure looks like, you can draw it this way. And this structure comes from a linear precursor called Geranil Pyrophosphate. And the pyrophosphate group is just a really good leaving group. Oops, what happened there? Nope, I do not want to update. Remind me later. Okay, so the question was, which of the isoprene units in the linear precursor end up where, and what new bonds did we have to make along the way? Okay, so I told you the way to begin is to identify the dimethyl tail in the starting material, and then to look for a carbon that's bonded to two methyl groups or something like two methyl groups in the product. And as we look for isoprene units, remember we are ignoring double bonds, and we are also ignoring heteroatoms like oxygen, just focusing on the sigma bonds. And then lastly, recall that, come on, that's better, that we've chosen to number the atoms of these isoprene units where the methyl groups are, we're calling carbon 3. So the bond that comes from the linear precursor is a sigma bond between carbon 5 of one unit and carbon 1 of the next. So do you see a dimethyl tail in alpha pinene? It's here or here? I'm seeing some skepticism. What do you think? I'm saying this is carbon 1, 2, and 3. Because I have a carbon 2 that is bonded to two methyl groups, and that's the same situation I have in the linear starting material. Okay, do you see that, or is that, what questions do you have about that? No? Yeah?
Could that be the other methyl group on the double bond?
Could it be this one? And the answer is, that is a branching methyl group, but it's attached to two other secondary carbons. So in the dimethyl tail, notice both of the carbons attached to carbon 2 are primary carbons. They're not attached to other things. So yeah, that's the difference. You are correct that the methyl group here is a branching methyl group, and we've talked about identifying those and calling them carbon 3. And then the carbon to which they are attached is carbon 2. All right, so we're working our way through. Once you identify 1, 2, and 3 on the dimethyl tail, then you have to choose what the next carbon is. You have to choose which one is carbon 4. And the choice is that whatever you choose to be bonded to, whatever you choose to call carbon 4 has to be bonded to 5, which has to be bonded to 1 of another isoprene unit. So as an example, what would be wrong about calling this carbon carbon 4? Go ahead.
The carbon 2 there would be carbon 5, and that's not right because carbon 5 doesn't have a branching group.
Good, exactly. So we can't call this carbon 4 because then it's the adjacent carbon which we would have to call 5, is actually carbon 2. So that direction doesn't work. So we can try the other direction. Let's call this carbon 4. Now let's see where we would put 5. Can we put 5 here? Would that work out? That would be a pattern that could work. Alternatively, some of you may ask, well, could I go here and then here? And that looks like that would work too. You're going to get in situations, and your text will show you this actually in a sample problem, that there are sometimes more than one way to assign isoprene units, and that's totally fine. What that means is there's more than one way to draw the mechanism that accounts for the formation of that molecule. And that's okay. And as long as your answer makes sense, it is correct. So how do you tell whether your answer makes sense? Again, the methyl groups have to be in the right places. And you have to have the right connectivity between 5 and 1. So for our purposes, let's say we've identified the dimethyl tail. So this would be the pink isoprene unit. And then this bond here would be the one between the two isoprene units. And then 1, 2, 3, 4, and 5. And so this then gives me an idea. I see a bond there between orange 5 and pink 4. That's not in the linear precursor. So that gives me an idea that I need to make that bond. There's also a bond between orange 4 and pink 2 that's not in the linear precursor, so I know I need to make that bond too. And so you can sort of see, once we make these assignments, you can sort of see the structure of the linear starting material wrapping around, sort of coiling like a snake around itself. And then we've got a couple of new bonds that we make along the way. Okay, questions about that? Yeah?
Alright, I'm still confused on how you identified the one in the center as the first isoprene.
Okay. So how you identify this one as the first isoprene unit? I looked for a carbon that's bonded to 2 methyl groups. Because my starting material has a carbon bonded to 2 methyl groups. And in general, the connections, the sigma bond connections in this linear precursor aren't going to change. We're going to make new ones, but those ones are going to stay in the product. So the only way I could have 2 methyl groups here is if they came from that carbon right there. Got it? Okay. Yeah.
So it looks like there's a double bond on the right side of the linear unit, like between carbon 2 and 4. Where does that bond go?
Where does that go? Good.
The orange one, sorry.
Okay. Where do either of them go?
That was my question.
Okay.
It was the dimethyl tail, that double bond. Where is that found?
Okay. We're actually going to convert that into a sigma bond, and I'll show you how. Yeah, as we fold this thing up and make new connections, in general, the chemistry is going to involve trading pi bonds for sigma bonds. And sigma bonds are more stable than pi bonds, so this can be energetically favorable. Good. And so, yeah, I'll answer that when we do that mechanism. What else? What other questions? Okay. So alpha-pinene is an example of a monoterpene. I'm going to show you a more complicated structure, and we're going to identify the isoprene units in it. So we need an anxiety-o-meter as I draw this so that I can sort of tell your stress level as I continue to put stuff on. We're not done yet. How are we doing? Pretty gross, huh? This is called cedrol, and it's a compound that can be isolated from cedar trees. Okay. And its precursor, if you count the number of carbons in Cedrol, it has 15 carbons. So its precursor is going to be a 15 carbon linear molecule. I'm going to abbreviate the pyrophosphate group like this. There are 3 isoprene units in this molecule, and sure. And here are the bonds between the two. And again, if you want to assign carbons, you can. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This precursor happens to be called Pharnaceal Pyrophosphate. And I'll show you later how you can make this from this 2 isoprene unit starting material. Okay, so 15 carbons, and we come into this process already having the bonds between pink 5 and orange 1, and between orange 5 and green 1. So the place we begin is first the dimethyl tail. So do you see a carbon that's bonded, sigma bonded to 2 methyl groups? It's that one right there. Okay, that stands out. So right away, you can label that in pink and say 1, 2, and 3. Now, there's a lot else we don't know at this stage, but we can look for the branching methyl groups. So here's one, and we'll call that 3, and this is carbon 2. Here's another branching methyl group, we'll call that 3, and this is carbon 2. We don't yet know where the rest of these isoprene units are. We don't know whether 3 and 2 is from orange or from green. Same thing over here. And we don't know which carbons are 4 and 5. So we're going to begin, and as we go along this process, you're going to see there's a couple of places where we could have chosen to assign the isoprene units in a different way, and that would have been fine. The idea, though, is we have to make sure that carbon 5 of one isoprene unit is sigma bonded to carbon 1 of the next. So let's begin with the dimethyl tail, and I want to ask, could this carbon be 4 or could that carbon be 4?
Are you looking for an answer?
Yes.
I'd imagine it has to be the one on the left.
Okay, you like that one?
I do.
What's wrong with this one?
That would put 5 at a spot where there's branching.
Okay, that would put 5 at the wrong spot where there's branching. Okay, good. Though, if I chose to curve around this way, 1, 2, 3, 4, 5, then this could be 1, 2, 3, 4, 5. But then how do I get the other isoprene unit on there? It needs to all be connected. So probably that's not a good choice. Then I could put 5 here. Then that would work because 5 of the pink isoprene unit is bonded to 1, and now I know this is the starting of the orange isoprene unit. Now, this has definitely got to be carbon 4 of the orange isoprene unit, but I'm not sure where 5 should go. What do you think? Could I put it here? Would that work? If this were 5, then 1, 2, 3, 4, 5. Okay. Or I could put 5 here, and then I'd have 1, 2, 3, 4, 5. So there's a couple of different alternatives there. Either of those are correct. The way we've chosen to assign it is this way. Then this is the bond between the orange isoprene unit and the green isoprene unit. Okay? So that answer works. And then the alternative would have been to call this 4 and 5 and this 1, 2, 3, 4, and 5. And you could make, if I asked you to draw a mechanism for how this molecule formed, you could have done it either way. One thing that's also useful at this point is to distinguish between bonds that were made during the process of going from the precursor to the product versus bonds that were already in the linear starting material. See, the red bonds between 5 and 1 here and 5 and 1 there are highlighted in our structure. And then the bonds that I'm highlighting in blue are bonds that we would have had to make as we convert the linear precursor into the product. If you look at the starting material, there is no sigma bond between 4 of one unit and 4 of another, so that's one we have to make. In the starting material, there is no sigma bond between 4 of one unit and 5 of another. That's another one we have to make. There's also no sigma bond between 2 of one unit and 4 of another. And then finally, there's also no carbon-oxygen bond. Incidentally, if you ask where did this carbon-oxygen bond come from, check it out. It's at a tertiary carbon. Likely that's water attacking a carbocation. All right, questions about how we identified those isoprene units? Okay, it makes a lot of sense when we do it together. The question is, can you do it on your own? So there's a lot of practice problems in the textbook. Give it a try. Now, let's talk about mechanism. And we're going to illustrate the kinds of mechanisms that you can see in terpene chemistry with the example of going from the starting material, Geranil Pyrophosphate, to alpha pinene. And along the way, there are going to be multiple branch points where it would have been chemically reasonable to do something else as well. And you will find that when we get to those branch points, those generally lead to other real natural products as well. So this is a highly versatile pathway. Nature can make a lot of different things this way. Now, a lot of the molecules we've been talking about so far are isolated from plants. And you can ask the question, why? What is the evolutionary purpose for this thing in the plant? Why does the plant want to make this compound? And the answer is, I don't know. But I bet they could tell you down in plant and wildlife sciences, if there is even a reason that's known. Sometimes you can isolate natural products from various sources in nature, and it is totally unclear at all why the bacteria or the sponge or some other thing might want to make that molecule. So that's an open question. But it's beautiful how nature can take simple starting materials and get to more complicated products. What we're doing now, today, is going to help us explain how we, humans, synthesize cholesterol. And we do it from these same starting materials. So instead of starting with Geranil pyrophosphate, I'm going to introduce the two biosynthetic subunits that are used in terpene synthesis in biology. This one is called dimethyl allyl pyrophosphate. Your text will call it diphosphate. Your biochem text will abbreviate this as DMAPP or DMAP or something like that if you insist on pronouncing it. And then the other is isopentenyl pyrophosphate, or we'll call that IP. And those are the two starting materials. So what kinds of reactions do we see along this reaction pathway? Well, let's start with dimethyl allyl pyrophosphate. One of the things you could notice is you've got a good leaving group and it's on a primary carbon, but That's not just any primary carbon, it is an allyl carbon. And hopefully from 351 you learned that leaving groups that are at an allyl carbon can leave to give a resonance stabilized carbocationic intermediate. So in many cases, leaving group leaves, sort of as an SN1 style reaction, is the initial step. So if we take dimethyl allyl pyrophosphate and the leaving group leaves, what have we got? Well, you look at that and say, oh no, that's a primary carbocation. Isn't that bad? And the answer is that's not just any primary carbocation. That is a resonance stabilized carbocation where the positive charge is simultaneously shared between the indicated carbons. And that's why it's reasonable for the pyrophosphate group to leave. Okay, so that's your SN1 step. Second step is the nucleophile, which is going to be a pi bond, a carbon-carbon pi bond, attacks the carbocation. Now, this is also something that you've seen similar things to before. This is sort of an addition to alkenes reaction. You remember in 351 learning that if you have this alkene and HBr, that the pi bond attacks the proton, and we make a new carbon-hydrogen bond with the less substituted carbons so that the positive charge can be on the more substituted carbon, which then bromine attacks to give you this product, right? What you haven't seen before, and you've also seen before a nucleophile attacking a carbocation. That's sort of SN1 chemistry. What you probably haven't seen before is the combination of these two, where a pi bond is the nucleophile that attacks a carbocation. So what does this look like? Here's our carbocationic intermediate that we got from the leaving group leaving from dimethyl allyl pyrophosphate. Here is the alkene from isopentenyl pyrophosphate. And what we're going to do is show the pi electrons from that carbon-carbon pi bond attacking carbon 5 of my carbocation. Now, at this stage, I usually get a question, why doesn't the pi electron attack at the tertiary carbon? Isn't there going to be more of the positive charge on that tertiary carbon than on the primary carbon? And the real answer is, I don't really know. You could calculate how much of the positive charge was on either of those carbons. The fact that the positive charge would be more stable here certainly has to be offset by the fact that the double bond is more stable there. So it's not totally clear. The other argument you could make is if you're going to have this pi bond attack the carbocation, it would be more efficient at the less sterically hindered carbon. The final explanation could be the enzyme makes it do it that way. That is sort of the hand-wavy cop-out answer, which we will revert to in many cases. So let's just take as a given that the pi electrons can attack and make a sigma bond with carbon 5. Now the question is, there were two atoms, 1 and 2, and we'll make this orange and this one pink. There were orange atoms 1 and 2 that are participating in the pi bond. Now, make a prediction. Which do you think of those atoms, orange 1 or 2, gets the new bond with pink carbon 5, and which one gets the positive charge? So here's my orange subunit. Here is the new bond I made. The question is, who gets it? Yikes. Better. Orange 1 or orange 2? What do you think?
So I'd say that orange 1 would be making a new bond, and that orange
Okay. And that should be better than the alternative because having the positive charge on a tertiary carbon is better than on a primary carbon, which would be the other option. Now, hold on, because I just hand-waved my way out of a primary versus tertiary issue up here. That's because of resonance. Resonance, these are not two different molecules. These are not two different structures. They are two manifestations of the same structure. In contrast, this is a isolated positive charge. It's not resonance stabilized. This is the familiar Markovnikov rule that you may have learned in 351, where when you do addition to alkenes, you do the first step on the less substituted carbon so that the positive charge in the intermediate can be on the more substituted carbon. All right? So that's an application of an old principle. Now, let's talk about what happens next, and this is sort of E1 style elimination of a proton adjacent to the positive charge. So if we take our product that we just made, the carbocation, and we have the positive charge here, I'm going to continue to highlight the individual isoprene units. If we zoom in and look at the carbons that are adjacent to the positive charge, we have 3 of them. Oh, that's kind of weird. That probably doesn't even show up on the screen. Yeah, that's fine. So we've got 3 protons adjacent to the positive charge. Now, in 351, what was the principle you used? How do you know which one is favored? It's the one that gives you the more substituted alkene because that's more stable. Okay, so that would tend to rule out the green one. Now, what about between pink and blue? Either would give a tertiary alkene, so you can't really decide based on stability there. So we have to fall back to, well, the enzyme prefers the pink one to be removed. But there's a chemical logic behind that, and that is that if you remove the pink proton and put the double bond there between orange 2 and 4, the product that you make will have its terminal leaving group also at an allyl position, such that if we wanted to, we could have that pyrophosphate leaving group leave to generate a carbocation, and we could do another sort of elongation step to make a longer molecule. So this molecule here is called Geranil Pyrophosphate, but if you repeat steps, if you repeat 1 through 3, you can get to the following molecule that has 3 isoprene units. And we'll highlight them here. And then this is called Pharnaceal Pyrophosphate. This has 10 carbons, this has 15. We get the green subunit by having this leaving group leave, then bringing in another molecule of isopentenyl pyrophosphate and having that act as a nucleophile and attacking the primary carbon. All right, so that's where you get the sigma framework for these linear precursors. Yes?
So when we're asked to do mechanisms for the practice problems, we first want to count the carbons in the product to know how many of these we need to connect.
Yeah, that's the question is, what about counting carbons? And that is a useful strategy. Count the number of carbons in the product and see how many isoprene units you need to have, and that'll tell you what your linear precursor was. Okay, others? So I told you that I would get to alpha pinene, but if you look, I've only taken you from these two starting materials to Geranil Pyrophosphate. So what happens next is going to involve more of these similar steps, but we're no longer going to be concerned with making the bonds between carbons 5 and 1. We're going to be concerned about making all the other bonds. So I'm going to copy our structure of alpha pinene that we wrote above. We've already talked about how to make the bond between 1 and 5. The bonds we're going to have to make on our way to alpha pinene are are highlighted in blue between pink 3 and orange 4, and between pink 4 and orange 5. All right. So I'm going to show you how you do this, and along the way, I'm going to show you an intermediate we need to get to. This is not something that I would expect you to be able to predict without ever having seen it before, but once you know, you should be able to work your way through it. The intermediate is this carbocation. And this is a precursor to a lot of different products. Nope, sorry, put the double bond in the wrong place. This is often called the alpha terpinyl cation, where you don't have to know that name, but we're going to first get from Geranil pyrophosphate to the alpha terpinyl carbocation, and then we'll get from that intermediate to alpha pinene. Okay, so it can be useful in trying to get from the linear precursor to the intermediate, again, to sort of identify what atoms you think are from, or what bonds are from the linear precursor and what bonds aren't. So with that analysis in place, it looks like we're going to have to make this bond between orange 5 and pink 4. Okay, and it can be helpful to redraw our starting material in a shape that sort of resembles the product, because that's going to tell us sort of where we need to go. So I'm going to redraw Geranil pyrophosphate kind of like this. Okay, so you can sort of see what needs to happen. We need first for the leaving group to leave so that we can get a carbocation. And then remember I said we want to make a connection between orange 4 and, between pink 4 and orange 5. And it seems reasonable to be able to do that because carbon 4, pink 4 is involved in a pi bond, so we could use that pi bond as a nucleophile to make a new bond between pink 4 and orange 5. The challenge here, though, is that if we made this bond directly, we would be making a 6-membered ring that looked like that, which having a trans double bond, I mean, on paper, you're like, okay, sure. But if you were to make the model, you would probably break some of your model pieces trying to get the bonds to connect. Or you would either physically break them or your molecule would just, you'd sort of get it and then it would fly apart. You can't have a trans double bond in a ring. Well, can we solve that? And one thing you might be thinking is, well, what about the resonance structure in which the double bond is here and the positive charge is there, can I then rotate around the bond between orange 2 and 4? And the answer is not as much as you think you can, because remember, resonance structures are not two different things. They are two partial representations of the same structure. So this double bond between the bond between 2 and 4 and between 4 and 5 both have double bond character. If you rotate around this bond, you're going to break the conjugation between the pi bond and the positive charge, and the positive charge just becomes a regular positive charge instead of a resonance stabilized one. That will be uphill in energy. So there is a barrier to rotate around carbons orange 2 and 4. Okay? So what's our way around that? And I don't know actually how high the barrier is or how slow that rotation is. But remember that the job of enzymes is to lower barriers or transition state energies to make the reaction faster. So what happens in the enzyme is that the pyrophosphate leaving group that just barely left will attack the positive charge will attack the resonance structure at orange 2. What this does, it looks like a step backwards, but what it does is it gets rid of the double bond character between orange 2 and orange 4. Now it's just a sigma bond. Now rotating around that sigma bond is free and easy to do. So we can generate, just by rotation, we can draw this conformation of the molecule. And then at that stage, the pyrophosphate group hops off to give us the carbocation again. Only this time, we've got the right shape of the molecule. Okay. So again, the reason why the leaving group leaves, hops back on the different carbon, is to make this process of rotating orange 5 to be close to pink 4. It's to make that process faster. Yes?
So how does this actually work in the lab? Does this leaving group leave is there like an equilibrium with that heat?
Good question. How do you do this in the lab? And the answer is generally these are enzyme catalyzed processes. People can do chemistry like this in the lab, but it's tricky. And what I'm showing you are the intermediates along the pathway that there's actually evidence for.
Okay, so this is all enzyme.
Yeah, this is all enzyme. There is evidence for this intermediate where the pyrophosphate group's now on orange carbon 2 because you can isolate that, and it's called Geranil Pyrophosphate, or at least that's what people have named it. And you can isolate it in some organisms or as part of this process. So that's, anyway, this is all, it looks like, what the heck are we doing? How would you know that this needs to happen? I'm just showing you what happens. And then the reason it has to happen is to allow for faster rotation around the bond between orange 4 and 5. Other questions? Okay, once we get there, carbon 4 in the alkene is next to carbon 5, the carbocation. We are poised for an intramolecular pi bond attacks carbocation. That establishes the 6-membered ring. Here is the new bond we just barely made. And as this step occurs, the enzyme biases this carbocation such that carbon 4 attacks orange 5 from below, so we end up with this stereochemistry. You would not have predicted that necessarily, but that's what enzymes are chiral and they can favor one enantiomer over the other. So if you compare back to where the intermediate we wanted to get to, this is that alpha terpinyl carbocation. Okay, so let's now compare that alpha terpinyl carbocation to alpha pinene and see where we need to go. As I'm checking things off in alpha, oops, that wasn't what we wanted. Circle, copy, paste. Okay, so checking things off again, I've made that bond in the linear precursor, and now I just barely made the bond between orange 5 and pink 4. Now what's the other one? I need to make a bond between pink 2 and orange 4. So let's just remind ourselves where everything is. 4 and 5. 1, 2, 3, 4, and 5. Okay. Well, if I need to make a bond between pink 2 and orange 4, you want one of those to be the carbocation and the other to be part of an alkene that can do the attacking. And it just so happens that we're totally set up for that. Do you see how the positive charge is on carbon 2? And then orange 4 is part of an alkene. So the molecule, the pi electrons on carbon 4, can actually reach around and attack carbon 2 and make the new bond. Now, I'm going to draw what that product looks like. And first, I'm going to draw it in a sort of distorted way that keeps the molecule in the same shape, but just sort of shows the new connections. Okay, so the new bond I made, and sorry, I'm going to continue to highlight things because that can be useful. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Sorry. The new bond I made will be between orange 4, and sorry, I need to try again. I'm going to only show in highlighting the bond that we've formed so that we can focus on it. So we make the new bond between 4 and 2. Probably because that pink 2 is down relative to the ring. Probably that happens on the back side underneath. All right, so now how do we rationalize this? Well, first, we still have the 6-membered ring, but because of the connection between 4 and 2, we just made a ring that has 1, 2, 3, 4 atoms in it. And we can redraw this. Oh, there would be a positive charge on carbon 2, right? Because the pi bond did the attacking. We can redraw this in a way that makes a little bit more physical sense, and that is to have pink carbon 2 underneath the ring and bonded to orange 4. Okay, so here are my two new bonds. Okay, questions about that? It's difficult to see in your mind how to get from here to here. If you want, you can redraw this molecule as follows. And that can make a little bit more sense. Okay? Yeah?
So is it the enzyme that's causing it to want to form that formula ring because aren't they usually really unstable? They have something
Right. The question is it the enzyme that's wanting you to make the four-membered ring or that directs you down that pathway? Yes. Others? Yeah?
Say you had a different enzyme, could you just go from that carbocation to some sort of alcohol, like attacking with water, or like have a bond right there on that too?
So could you, here you mean?
Yeah, just like end that.
Yes. Can you do other things from this carbocation? Yes. Could you have an alcohol attack there? Yes. I don't know what that product is or whether any organism makes it, but it's reasonable. To finish the thing with alpha pinene, actually, all we need to do is an E1 style elimination to create the double bond there, and that's alpha pinene. Now, if we had done the elimination from carbon 3, we could have gotten an isomer of alpha pinene, which is called, surprisingly, beta pinene. And you know, what controls that? Well, the alkene in alpha pinene is more stable. Why does nature sometimes make beta pinene? I'm not sure. But could you push arrows if I told you which one was the product, right? Yes?
So is there a reason why we wouldn't take the hydrogen off of the orange carbon 4?
Is there a reason we wouldn't take the hydrogen off orange carbon 4? The answer is that the geometry doesn't allow it. So orange hydrogen 4 is here, whereas the empty p orbital is here, and they don't align with each other. You can only do eliminations when the protons adjacent to the positive charge can line up with the empty p orbital. Okay. So that's fun. I want to show you some other things that can happen. To do this, we're going to raise the specter of an old friend from 351, that is the 1,2 hydride shift, carbocation rearrangement. If you do the 1,2 hydride shift, you convert that carbocation into another one. And then you can get from that intermediate to a molecule that looks like this. Which, if you sort of squint and look for a certain look through imaginary and figurative lenses, sort of looks like a duck. That's called alpha-thugine, and I think you can find it in thyme and some other herbs. But there's a whole bunch of other things that can happen. For example, you can make limonene from this intermediate. Ultimately, menthol comes from that intermediate too. Somebody asked her in the first hour, could I instead remove a proton from this carbon? Could I remove a proton from this carbon and make something that has a conjugated diene in it? And the answer is absolutely. All of these things can happen. There are enzymes that direct them to happen, but the point is it involves steps that are relatively simple. Now, your assignment for this weekend is to figure out a reasonable mechanism for getting from this precursor to cedrol. Yeah, I'll put it in the notes. Focus on the bonds you have to make during the process, and I will see you again on Monday. May the force be with you.